So, where did we end up last time? Last time we discussed the Kahn-Ingold-Prelog rules for determining absolute configuration at a chiral carbon atom. And that's, by the way, I'll just also mention, it's not going to be wasted time. We're going to use the Kahn-Ingold-Prelog rules again in, I think, chapter 7 to learn about E and Z configuration in alkenes. So it's something we'll apply later. It's not going to be a waste of time. But we learned in applying those rules that we have varying methods or tools we can use when we're looking at a problem where something's maybe not given us in the most convenient way possible. You know, what do we do if the lowest priority group is not on the dotted line bond? And so we learned some methods to deal with that. And then we introduced the idea of the 2 to the n formula, or 2 to the n rule, which says that a compound with n chiral carbons will have at most 2 to the n possible stereoisomers. And that's what we're going to tackle today, is how to deal with it when there's 2 chiral carbons in a molecule. Well, 2 to the n in that case is 2 squared, which is 4. So that tells us there's 4 possible stereoisomers maximum. And we're actually going to look at that type of situation today, when there are 4 distinct stereoisomers. And I've given you an example of one of those here on the whiteboard. So we're going to analyze those. We'll figure out what the absolute configuration is of all of the chiral carbons, and we'll learn how to compare these different stereoisomers. We already know what enantiomers are, and so we'll also introduce this idea of diastereomers. And then last time, I think I also introduced this idea of how we can draw structures like this when there's more than 1 chiral carbon. This type of structure actually leads straight into the Fisher projections. Like I said, your book is the first that I've encountered that does not introduce Fisher projections now, but as I've been through it in this book for a few years, I'm a fan of the idea. I get what they're doing, and I think I like their idea, because otherwise every other textbook I've ever taught from goes straight from this into Fisher projections, and then you hear nothing else about Fisher projections until organic 2, you know, however many months away that is, when we talk about carbohydrates. And so then I say, you guys remember about Fisher projections, right? And everyone's looking at me like I'm completely insane. So I'm a fan of this idea. For now, we'll use this convention of drawing molecules with multiple chiral carbons. And I do need to say, when we use this convention, call it what you will. I don't really have a name for it. If you want to call these pre-Fisher projections, I don't know. I'm okay with that. But I do need to make it clear that when we draw structures using this convention, they have to look exactly like this, not in terms of the groups attached. Of course, we can change all of those groups to whatever we want. But in terms of the way the bonds are, they need to look exactly like this, or it's wrong and you'll lose points. By that I mean that we need to make sure that the wedge bonds are horizontal and the dotted bonds are vertical and on the end. So it has to be just like that, or it's wrong and you'll lose points. You're not allowed to just change wedges to straight lines or dotteds to wedges or anything like that. It has to look just like this, with the wedge bonds horizontal and the top and bottommost bonds both being dotted lines. It has to look exactly like that, or it's wrong. And once we're used to that convention, yes, learning about Fisher projections next term will be fairly easy to do, I think. But we'll postpone that until then, and we'll just use this convention for dealing with molecules with multiple chiral carbons. Good. Well, that there are 4 possibilities for where to put the OHs on these 2 chiral carbons, I think is fairly evident. And that leads directly to 1 pair of enantiomers here. I think you can all see that we've got like a mirror plane going down the middle. And these 2 stereoisomers are mirror images, and so they will turn out to be enantiomers. There's also yet another pair of enantiomers over here. Just let me double check I did that right. Yep, looks good. So those 2 are also mirror images, and they will also wind up being enantiomers. And so we'll compare the idea of enantiomers to the idea of diastereomers today. But the first thing I want to go over is, or the first thing I want to do is figure out what the absolute configurations of all 8 of those chiral carbons are. And the great thing is, when you're in a situation like this, really you only have to do it for one of the 4 compounds, or for one of the stereoisomers. Because once we figure out for one of them, the others we can get just by comparing. So that's very convenient. But I do want to take some time to go over figuring out that stereochemistry. But before then, I promised that I would prove to you that this is an okay way to draw structures. And I said I would need my molecular models, which I've brought with me this time. So the reason I'm going to do that is it's been my experience that a significant percentage of students need me to show you that this is okay. Because otherwise it just seems, probably because it just seems like this arbitrary rule that I'm just enforcing on you. We got this thing and the wedges are to be here and the dots are to be there, and you know, you just have to learn it, live it, love it. But I want to prove to you that this is an acceptable way to draw compounds with multiple chiral carbons, and prove to you that this is actually meaningful to draw it like that. So that's what I'm going to do with molecular models. I have a molecular model of this compound ready. So that's what I'm going to do next. Any questions before I do that? I think I said this in my other class once too. I feel like the priest at the beginning of that old movie, Sister Act. Good morning, O ye few. Guess they're mostly on chat. Good, okay, well, first I have to switch over to the document camera. I think I know how to do that now. Those of you in person can already see my molecular models. Those of you in chat, I think I need to do this for you. Yep, and then you can see it. At least, right? Can you guys in chat see my model? Oh, good, thank goodness, okay. I love it when things actually work. So I've made a model of that compound over here, and you can compare this to the structures that I've just drawn. So here at the top, that's my aldehyde functional group. You can see C double bond O and H. So it's another thing that maybe if you didn't know, you need to write down so that you know it. CHO is an abbreviation for an aldehyde group. And the reason we do CHO instead of COH, well, that sounds like an alcohol. So if you ever see CHO, it means it's an abbreviation for an aldehyde group, just like COOH or CO2H is an abbreviation for a carboxylic acid group. And again, you do not have to use CHO to designate an aldehyde group if you don't want to. All I ask is that when you see these abbreviations, you understand them and they mean something to you. So anyway, here's our aldehyde group. We'll go to the next carbon, and you can see that bond is going away from us. And that carbon has a hydrogen on the left and an OH on the right. And they're both coming out at us. Can you see how those 2 bonds are coming out at us? So hopefully I'm convincing you that this model is the same as the structure I gave you. Then, when we go to the next one, same thing. We've got 2 bonds coming out at us. This one's a hydrogen, and that one's an OH. And then when you go to the next carbon, that carbon's not chiral, it's just CH2OH, and it's pointing in the back. So can you see how these bonds are pointing out at us? They're on wedge bonds, and then these other groups are on dotted bonds because they're going into the plane. Does that make sense? If I satisfied you, have I proven to you that with this model, that shows that that's an okay way to write structures? Does that make sense? Have I satisfied everyone? Questions on that? So I mean, I appreciate your putting up with me, but I just have learned over the years that if I don't go through that, then it just sounds like I'm imposing this rule on people. So now that I've satisfied everyone, now, all of that being said, granted, this is most certainly not anywhere near the lowest energy conformation, right? Everything's eclipsed. So it's not the lowest energy conformation, but it is an okay way to represent that molecule. You know, really the thing would probably do something like this more often in solution. But that's an acceptable way to draw structures. And we'll use that, as I said, next term when we start drawing sugars. And by the way, this compound indeed is a sugar. It's a 4-carbon sugar. And I should know what that's called. I forget if it's erythrose. I can never remember these things. But One could look that up. That's not even the sort of thing I would expect you to memorize next term, since I don't have it memorized myself. Okay, so now that we've established that this is an acceptable way to draw structures, let's tackle the issue, since you'll get asked this on OWL as well, of what are the absolute configurations of all 8 of those carbons using the Conin-Gold-Prelog rules. And once again, oh, you looked it up, it's erythros, thank you. Is that what I said? Wow, I'm almost impressed with myself. Maybe, I wonder if those guys are 3Os, but in any case, right, be that as it may, once we figure out 2 absolute configurations on one of these 4 compounds, then we automatically get the others thrown in for free. So that's a good thing. And so we'll do it the usual way. I do want to point out that we've got an issue, and this is why I also stressed that you're not allowed to change the directions those bonds point. It has to look exactly like that in a compound with 2 chiral carbons. One could go on, of course. You could put a 3rd chiral carbon and a 4th, and so forth. If we have time, I'll draw the structure of D-glucose for you later and show how we do that. But be that as it may, the problem is our lowest priority group, our hydrogen, is on both of them on a wedge bond. It's in exactly the wrong place. And so we talked about a few tools we could use to deal with that. This is where my student from 20 years ago, that I only remember her name is Rochelle, this is where Rochelle's method really works. Because if you now go run behind that structure, well, now those hydrogens are facing away from you and everything is as normal. So those of you who want to follow in Rochelle's footsteps can certainly do so. But you don't have to. I put a rule down here, which is that if the lowest priority group is on a wedge bond, then that means that we'll go through all the steps like we usually do, step by step. But we just need to remember at the last second to change our minds. Since the lowest priority group is on a wedge bond, that means if we were going to say S, if it's a left turn, we'll call it R. And if we were going to say R because it's a right turn, we'll call it S. And that will always be the case. There will never be any exceptions to that when the lowest priority group is on a wedge bond. It's another way of dealing with that situation. And it's one that it's the way I usually use it when I'm in this type of situation, where we see our lowest priority group on a wedge bond. I do need to add to that, though. There's a caveat there that I need to add, which is if you're given a problem where the lowest priority group is on a straight line bond, neither a wedge bond nor a dot bond. You know, dot bond and you're good. Wedge bond and you can just do this, you can just flip it, or use any of the other tools we used last time. But if the lowest priority group is on a straight line bond, which you could get, then there is no shortcut that I know of. This only works when the lowest priority group is on a wedge bond. I do not know, I have failed to find any shortcut for when the lowest priority group is on a straight line. Then you have to do one of the things we talked about last time. You could do a modified Rochelle's method. You could, where you go to the side of the thing instead. You could switch 2 groups, just being aware that, again, that will flip S to R and R to S. Or you could rotate around one of the single bonds until your lowest priority group is on the dotted bond, for example. So I don't know of a shortcut when the lowest priority group is on a straight line. I do not recommend trying I do not recommend trying to find one. I mean, I want you guys to be curious, but I've been over it a number of times and I have to date failed to find one. If there's one that works, fantastic. I just don't believe that there is. So when the lowest priority group is on a straight line bond, you have to redraw the molecule. I don't know of any shortcut, but this shortcut here works if the lowest priority group is on a wedge bond. And I think we kind of hinted at that on Monday. So that's what we'll do in order to assign those configurations. What I've done is I've separated out these 2 carbons so that we can consider what they're attached to separately. And the reason, for instance, that I drew those bonds as straight lines is because we're not considering the stereochemistry there. So we don't care what's on a wedge and what's in the dot. We're only considering the stereochemistry of this carbon. Over here, we're only considering the stereochemistry of this carbon, so I don't care what's a wedge or dot bond on those. All I care is what it's attached to. And so, so I hope that I can show you a way to deal with this type of thing in a fairly straightforward fashion. Good, but that's what I'm going to do next, is we're going to apply the Conan-Gold-Prelog rules to those two carbons. Everyone okay so far? How are we for time? Got a little, yes. I'm sorry, I couldn't hear. Right. Mm-hmm. The question was if the carbons attached to 4 different groups, it's chiral. Yes. A good question. Can something other than carbon be chiral? Yes, that does happen. We'll probably talk a little bit about things like that the next time after we deal with the wild and woolly and wonderful world of meso compounds. I'll probably say a few things. I don't think it's something we're going to run into too often, though to give you a direct answer to your question, I don't think it's going to come as a shock to anyone. Yes, someone even put it. I don't think it's going to come as a shock to anyone that silicon can also be chiral. It's right below carbon in the periodic table, so it can form 4 bonds the same way. And yes, absolutely, chiral silicon compounds are known. I don't think we'll ever see any of them, but you would deal with it in exactly the same way. Same rules, same method, same everything. You could also, and I think they've also made chiral germanium compounds. Germanium's right below silicon. Tin, I don't know, maybe. Tin's already a metal, so I don't know. I don't know about that one, but certainly for sure silicon and germanium. Okay, so let's then go ahead and assign R and S, R or S to those 2 carbons. So let's just consider the green circled carbon first. The oxygen's clearly top priority. Oxygen's element 8 and carbon is element 6, so oxygen's clearly top priority. Lowest priority, equally obviously the hydrogen, no problem. But here, those 2 groups are both carbons, so it's a tie. So we need to break that tie, and the way we do that is by considering what's attached to each of them. And so sometimes students have told me that they're helped if they write down and list what each of those 2 carbons that are otherwise in a tie, what each of them is attached to. So this carbon looks to me like it's attached to 2 carbons, a hydrogen and an oxygen. So you could write down HCCO. Other students have told me that they don't even bother counting that carbon-carbon bond that's to the chiral carbon that we're considering, because both of those carbons, both of those atoms have that type of bond in common. So they'll just count the other 3 groups, HOC, HCO. You can do that too, whichever you prefer. You'll come up with the same answer. What about this one? We've got C double bond O, and remember the rule, C double bond O is like C with 2 single bond O's. So every time you see a multiple bond, it's as if you had that many single bonds to the same type of atom. That goes for all double and triple bonds, with no exception. So that's part of the Conan-Gold-Prelog rules. Anyway, when I do that, now it looks to me like this carbon is bonded to a hydrogen, a carbon, and 2 oxygens. Or again, if you weren't considering the carbon-carbon bond, then it'd be a hydrogen and 2 oxygens. You'll get the same answer either way. You can look at it either way. And so now we need to break this tie. Well, we're not going to do it with the 2 H's, that's a tie. We're not going to do it with those 2 oxygens, that's a tie. These 2 carbons are a tie. And we're left with an oxygen versus a carbon, and the oxygen on this top carbon wins, right? Oxygen's element 8, carbon's element 6. So that means this carbon is 2nd priority, and that carbon is 3rd priority. So now, we'll go ahead and turn our steering wheel as usual, but we'll remember this rule over here. You know, our stupid, stubborn, naughty hydrogen is on a wedge bond. So that means we got to change our mind at the last second. So I'm going to, ignoring the 4, go the shortest way from 1 to 2, 2 to 3, and 3 back to 1. That looks to me like a left turn. It's counterclockwise. But we got to remember at the last second, because the lowest priority group is on a wedge bond, it's not S, it's R. You just got to remember to do that at the last second. And again, there are other ways to deal with this type of problem, but that's one way. So that means that carbon is also R. And we'll do the other one too. So you'll get to see another example of this whole thing in action. Does that make sense? Any questions on that? You mean I did it again? That was so clear that no questions are possible. I wish. I wish that were true about me. Okay, so let's then look at the blue circled carbon. So again, clearly oxygen wins, that's top priority, hydrogen lowest priority. But again, we've got a tie between these two carbons. So we need to consider what each of those carbons in turn is attached to. And by the way, if that were still a tie, as we mentioned the last time, we'd need to go out yet another set of bonds until we could break the tie. But I think we're going to break the tie here. So this carbon looks to me like it's attached to two carbons, an oxygen and a hydrogen. So I'll write H, C, C, O. Of course, it doesn't matter what order you write them in. Meanwhile, this carbon is attached to one carbon, two hydrogens, and an oxygen. So we're going to have two hydrogens, one carbon, and one oxygen. Well, the oxygens will tie, these hydrogens will tie, and these two carbons will tie. And so you're left with a carbon versus a hydrogen. And so, of course, the carbon wins. Carbon's element 6, hydrogen's element 1. So that means that this carbon is second priority and the CH2 third priority. So now when we go ahead and turn the proverbial steering wheel, we'll ignore the 4, we'll go the shortest distance from 1 to 2, 2 to 3, and 3 back to 1. So that looks to me, once again, counterclockwise, it's a left turn, but the naughty hydrogen is in a wedge bond. So even though it's a left turn, we'll change our mind at the last second and call it R. And so I conclude that compound is the RR enantiomer. Or if you were being picky with numbers, you would call that the 2R, 3R enantiomer, because carbon 1 is going to be this aldehyde functional group. We'll learn about that again next term when we learn how to name sugars. It's always going to be the case that so we don't consider that hydrogen attached to the O in third priority. Yes, good. We don't even care about that because we can make our decision. Does everyone see the question in chat? Yeah, we don't even care that this is attached to hydrogen or over here for that matter. That doesn't matter because we can make our decision without worrying about that. In other words, we make our decision before getting to that atom. So I would say, yeah, I would say what you just said is exactly right. That's a good point. Good, so RR. So this is the RR enantiomer. And the great thing again is once we know that, the others are all thrown in for free. We just get them by inspection. So this one must be SS since it's exactly the opposite. On this one looks to me like the bottom one's the same and the top one's flipped. So that one must be SR and this one must be RS. So although it's a little tedious to do it for one of the stereoisomers, the great thing is once you do that one of the stereoisomers, you get all of the others thrown in for free. So what does this mean then in terms of our definitions? We've already said that we've got 4 distinct stereoisomers here. 2 squared is 4, so there's a maximum of 4, and indeed we have 4 stereoisomers. All 4 of those are different compounds. And we already know that the RR and that this pair here, the RR and SS stereoisomers, those are going to be enantiomers. Or again, if you wanted to call them 2R, 3R, and 2S, 3S. But I think it's clear enough this way. You'll know what you need to put based on how the question's phrased. So those are enantiomers. And we also have that the SR and RS compounds are enantiomers. So we have 2 pairs of enantiomers. And this is, I would say, by far the more common of the 2 possibilities when you've got 2 chiral carbons, is you find that they exist as 4 stereoisomers in 2 pairs of enantiomers. And there's another thing that we can get from this that's very important and that you will surely need to know, is that when you turn something into its enantiomer, how do you know which to put first when it's RS and S? Well, again, that will depend partly on how the question's phrased. That will tell you what you need to put. But in this case, I'm listing it this way because the aldehyde carbon is carbon 1 in sugars, which we don't know yet, but we don't need to. I think there's enough information here to make that decision. In any case, if you label the carbons directly like this, then it's unambiguous. So then you'll always know what to do. But again, the way the question's phrased will tell you what you need to put down. Good. So, but you'll notice that when you change any given stereoisomer into its enantiomer, you interconvert all of the R's and S's. So RR becomes SS, SR becomes RS, and vice versa. That will always be the case. There are no exceptions. Whenever you go from one enantiomer to another, all of the R's and S's interconvert. But what if they don't all interconvert? Like, what about these two, the RR and SR, RR and RS compounds? That's where diastereomers comes in. And any other pair that you can make among those 4 stereoisomers, those are your diastereomers. And as I think I might have mentioned the last time, if you're upset with this word because it's nowhere near long enough for you, you may also call them diastereoisomers. That's also an acceptable term, if you just need the word to be longer for whatever reason. Anyway, I would say the definition of diastereomers is 2 stereoisomers that are not enantiomers. They're not mirror images. They're distinct stereoisomers, but they are not mirror images. Enantiomers will always be mirror images by definition. But I think you'll agree any other pair you might pick, like these 2, let's say, those are not mirror images. And the way I know that is because on one of the corresponding carbons, the absolute configuration is the same in both of them. They're both S on the bottom carbon. So those 2 cannot be mirror images. And so that's what we mean when we call 2 compounds diastereomers. And so in the end, what we have here is 4 stereoisomers that exist as 2 pairs of enantiomers. And again, that's very common, probably by far the more common of the 2 possibilities when you've got a compound with exactly 2 chiral carbons. We'll get to the other possibility next time. Yes? Is it possible to have diastereomers when there's only 1 chiral center? Excellent question. Answer is no, because if there's only 1 chiral center, 2 to the first power is 2. You have 2 stereoisomers. They're enantiomers. So that's a good question, though. Diastereomers only come up when you have multiple chiral carbons. So if there's just 1 chiral carbon, you just have a pair of enantiomers, and that's it. That's the only possibility. No, good question. Other questions? Good, so I think that's my last main point for today, is this idea of diastereomers. They're defined as 2 or more stereoisomers that are not mirror images of each other. And so any other pair that you make of those 4 compounds that's not enantiomers would be diastereomers. But the weird thing sometimes happens, and I think this is what we'll run into in the next class. Maybe then I'll end with our reef polling, or our what you call it? Yeah, polling, because I have some questions for you. Please do register your attendance if you haven't, because that's going to be 8 out of the 10 points. But what we'll find next time is, with some tweaks to the structure of these things, you wind up with a situation where it looks at first like you have 2 pairs of enantiomers again, just like this one. But then when you look more closely, lo and behold, 1 pair of enantiomers is not a pair at all. Instead of a pair of enantiomers, they turn out to be 2 different ways to draw the same compound. It's just 1 compound. That is bizarre, but it happens sometimes. And I think we'll also be able to learn something about how to tell when that's going to happen, so you can see it coming. Those are called meso compounds, and we'll deal with that can of worms the next time. And again, like someone asked about chirality at atoms other than carbon, we'll probably talk a little bit about things like that as well. Can you do an example of redrawing a molecule that is the lowest priority group in a straight line bond? I thought we did the last time. But also last time, I don't know if I have time to do that today, but I gave you some tools that you can use when that happens. You can grab one group and rotate around the bond until your lowest priority group sticks in back. That's one thing you can do. Last time I did give a bunch of different methods that you can use. Maybe you want to switch two groups, and then just remember that when you do that, you flipped R to S and S to R, and then figure out by implication what your original structure was. So that's, I would use one of those methods, whichever one works best for you if you run into a situation like that. So let's move into polling. Let me see if I can pull up PowerPoint, and we'll do a slideshow from beginning. Good. So, so my first question for you guys today, a compound with 4 chiral carbons would have a maximum of how many possible different stereoisomers? And yes, you may use a calculator if you like. I don't think you'll need one, but I would rather you use one than not use it and get it wrong. Oh, also to the most recent question of redrawing a molecule that is the lowest priority group in a straight line bond. I just don't have time to do every single possibility, but you know owl will be owl by now. I'm quite sure they will be evil enough to give you a case like that to practice. I'm starting to think that's one of their necessary traits for people who write their questions. Must be evil. So we'll go out to 2 minutes. Fifteen more seconds. Last chance for answers. Anyone else? Looks like we're maxed out at 119. Okay, well this one's hopefully fairly straightforward. I think we can dispense with it pretty quickly. So again, recall the formula for the maximum number of stereoisomers possible if you have n chiral carbons is 2 to the power n. Last I checked, 2 to the 4th power is 16. So I think that should be C, as did you. Good. Next one, a little bit more brain work involved. Press A if the following chiral carbon is the R configuration. Let me move my picture so you can read it. B if the S configuration. Please do not put C, D, or E. Oh, can you not see? What, sorry? I don't know what to do about that. Maybe, yeah, I don't know what to do about that. Well, let's try this. Let me get us out of here. Let's just start it over. Oh, look at Zoom. Okay. Yeah, I don't know why it's doing that. You might just want to look on the Zoom screen. Yeah, if you look on Zoom, you should be able to see it because it's on our screen here. You know, I don't know what to do about that. This is the first time this has ever happened to me. It certainly worked in the last class. Yeah, those are the only two answers. Yes, just A or B. A for R, B for S. And you can see the structure. I'll let this go to 3 minutes. You can see the structure on the Zoom screen. That's really weird. It worked fine in the last class. All right, 15 more seconds. Yeah, we've got the same number of responses, so I guess it's fine. Anyone else? Last chance. Looks like that's it. Well, what I'll do is I'll switch. Wait, where's? Is I will switch back to my whiteboard and let's work it out. So, correct me if I'm wrong, but as I recall, we had an isopropyl group. I think I needed to go the other way. And then we had a naughty hydrogen coming out at us, and our bromine wasn't back, being very unhelpful. I think we had something like this. And as I said, we have varying ways of dealing with this. One thing we can do is just flip it in the plane, just flip it 180 degrees, and that will put the ethyl group over here. Now our bromine will be in front, and our hydrogen will be helpfully in back, and our isopropyl group will be over here. That's one way to do it. It's not the only way, but that's one way to deal with it. And so this way, now the hydrogen's of course 4, bromine obviously priority 1. And then when we compare the other two groups, the isopropyl group has to win. This carbon's bonded to 2 carbons and 2 hydrogens. This carbon's bonded to 3 carbons and 1 hydrogen. So one of those carbons will trump the hydrogen, so to speak. So it looks to me like this is going to be second priority, that one third priority. And now when we go turn our steering wheel, so to speak, we ignore the 4, 1 to 2, 2 to 3, 3 back to 1. That looks to me like a right turn. So it's R. So with that, now I need to go back to, I think that means we wanted to put A, but let's just double check that. Yes, A if it's R, B if it's S. So I think A is the better answer, as did you guys. Wait, I'm sorry? Well, it's the same compound. Well, it's the same, because, but all I did is I took it and I flipped it like this so that the hydrogen was pointing in back. You could also go from here, and you could use that same method we did. You could say, well, I'll turn my steering wheel with my dumb hydrogens on the wedge bond, and so I have to change my mind at the end. You would find that it's a left turn, but you change it to R. So I think you'll get the same answer. Anyway, with that, I think I'm out of time. Why did you have to flip it? Oh, the reason I had to flip it is because my hydrogen was naughty and on the wedge bond. You don't have to flip it if you don't want to. Like I said, there's several different ways to deal with that, and you can just use whichever works the best for you. With that, I'm definitely out of time, so I will see all of you on Friday. Have a great day.